Well, hello, good people. Today we are talking about buoyancy and Archimedes' principle. I love Archimedes' principle, and I remember first learning about Archimedes' principle, and it absolutely blew my mind, and here's why. Learning about buoyancy and Archimedes' principle has everything to do with whether an object floats or sinks. And prior to learning Archimedes' principle, I thought that I knew what made an object float or sink. I thought I knew that it was like if it was a less dense object, then it floats, and if it's a more dense object, then it sinks. And so I thought that that was something that I knew, and I felt pretty confident in it, and I would have said, yep, that is a done deal. That is all good to go. I think in my brain, I think I understand that one pretty clearly and perfectly, and there's nothing really more to understand there. But then I learned Archimedes' principle, and I learned that this concept that I thought was pretty much just like done deal, we're good to go, was actually deeper than that. There was more depth to it. There was more interesting stuff to find the digger that you deep? The deeper that you dig with the concept of Archimedes' principle and with buoyancy. And I just love that because that's true about all things. Like you think you know something and then you continue to think about it or you continue to study it and you find out that actually you didn't know how well you didn't know it at all. So that's why I love Archimedes' principle. It's just a total reframing of something that you think you know. Now, when we're talking buoyancy and Archimedes' principle, we are talking about why things float. And it is actually helpful to remember the old things that you know. You know that things float based on their relative densities relative to one another. If you have something that is less dense in a fluid that is more dense, the object will float. And if you have an object that is more dense in a fluid that is less dense, the object will sink. But there's a little bit more depth that I want to look at here. And I'm going to start with your childhood bathtub. You remember your childhood bathtub times? It was a great time for all of us. It was the time when you would get in the bathtub and you would play with your favorite bathtub toy, which is the plastic cup. We remember this. You take your plastic cup and you put your plastic cup inside of the water. And here's what was always fascinating to me is that I gotta redraw that cup. That's just a terrible cup. No, you can't even tell that that's really. Oh gosh, no, not the water. Oh wow, refill the bath. That was the fastest bath fill you've ever seen in your whole life. Okay, here we go. You got the plastic cup. I think I made it worse. It doesn't matter. Plastic cup is in the water. Now this was always fascinating to me that I would take the plastic cup, I would dunk it down into the water, and I would dunk it down like the bottom at the top. And I would dunk it in, and it would go flying back up towards the surface. And I always thought, that is just the funnest, greatest thing I've ever seen. I love that my cup does that. I push it down, it springs back up. I push it down, it springs back up. I push it down, it springs back up. And I thought, wow, bathtub time is great. But really, the true greatness of bathtub time all comes from Archimedes' principle. Now, here's the question. Why does this cup go flying up towards the surface of the water and up out of the water? What is pushing it up? Well, let's take a little look here at this diagram. Yesterday, we learned about pressure with depth. And we said the deeper and deeper and deeper down you go, the greater and greater the pressure is. Well, that means that right here, the water that is right here has to hold up this much water above it, and so that's a pretty good amount of pressure. But the water that's right here has to hold up this much water above it, and so that's even more pressure because this water down here has to hold up the weight of all this water, and this water up here has to hold up the weight of just this water. Likewise, you could talk about it other ways too. You could talk about it in terms of, oh wait, that's not what I want. Okay, you could also talk about it in terms of not like how much water the water has to hold up, although it's true, this water down here does have to hold up all of this water, and this water up here has to hold up just this much water. But you could also talk about how much pressure there is based on how much water is pressing down. So up here at the top of the cup, you have this much water pressing down, and then down here at the bottom, you have this much water pressing down. So you have different pressures in each places. And one way to think about it is that this part of the water has to hold up all the water above it. Or another way to think about it is that this part of the water is getting pressed down by all of this water above it. Now, Newton's third law says that for every action force, there's an equal and opposite reaction force. As hard as the water presses up, that's how hard the water also presses down. So two ways to think about the same thing. Now, here's what happens right now to this cup. And I think you're kind of going to see where this is going. Do you see how the top of the cup, which we shall call is at height 1? The top of the cup is experiencing, when this thing is in the water, a different pressure than the bottom of the cup. The bottom of the cup is experiencing a pressure on this surface, and the top of the cup is experiencing a pressure on this surface, and the pressure that the top of the cup and the bottom of the cup are experiencing is different in size. The bottom of the cup, because it's lower down in the water, is experiencing more pressure than the top of the cup. And Pascal's principle tells us that the direction of that pressure is always perpendicular to any surfaces that are there. So, the top of the cup is currently being pushed down by the pressure. And it's being pushed down by pressure, I'll call it P1, because there's water on top of it that's pushing it down. The bottom of the cup is currently being pushed up because the water below it is holding up the whole weight of the water above it. And so it's pushing up on the cup, just the same way that it's pushing up on the rest of the water. So the pressure on the top is down, the pressure on the bottom is up. But now the question is, there is a battle between the pressures. The top of the cup is getting pushed down, the bottom of the cup is getting pushed up, but which one is winning? The bottom pressure, because you have more pressure at a lower spot in the water. So down here, this bottom pressure is winning. This means that the net change in pressure, or the net difference in pressure, is going to be directed upwards because the pressure is greater lower and less higher up in the water. So this means that the cup is actually getting pushed upwards by the pressure. This pressure results in what we call the buoyant force. The buoyant force results from the differences in pressure between the bottom of the object and the top of the object. And because the pressure on the bottom is greater, the object gets pushed upwards, and we call that a buoyant force. Now, technically, if you really wanted to calculate the buoyant force, you would say that pressure, or a change in pressure, is equal to a force per area. So then the force is really the change in pressure times the area. And now we're going to do a really nice derivation that is actually going to lead us to Archimedes' principle. This is not Archimedes' principle yet. This is just the concept of the buoyant force, but we're going to get there. Let's take a look here. We say that the force that this object is experiencing is the difference in pressure between the top of the cup and the bottom of the cup times the area that's experiencing that pressure. Well, the pressure on the bottom of the cup is going to be rho g h2. And the pressure on the top of the cup is going to be rho g h1. And so that's our difference in pressure here between the bottom of the cup and the top of the cup. And we multiply that by the area that is experiencing the pressure. Do you see how the area that is experiencing the pressure in this case is going to be the base of your cup or the top of your cup? Either way, it's going to be the area of the base of the cup. If the cup is a nice little cylinder here. Well, check it out. We got a rho and a g here that's true in both terms. So we can pull out that rho g, and I'm left with an h2 minus an h1. Hey, isn't h2 minus h1, isn't that the height of the cup? Isn't that what the height of the cup is? Is it's this difference in height here, this little delta h? So I have this rho times g times this delta h, which is the height of the object. Or in this case, the height of the cup. Hey, check it out. We got a rho times a g times an area of the base times a height. An area of the base times the height, that gives me the volume of the cup. And now, here's the very last move that we're going to make, and this is what's going to bring us to Archimedes' principle. Do you see that when this cup goes into the water, it's going to displace some water? And when we say displace some water, we mean move some water out of the way. So there was some water here. You know this when you get into the bathtub. You get into the bathtub and all the water level rises, and the water level rises, and we call that displacement. It's how much water you move out of the way. Well, the volume of the cup is the volume of the water that is displaced by the cup. They're the same volume because the cup pushes the water out of the way that is the same amount as the amount of space that the cup is taking up. So we say that's going to be the volume of the water that gets displaced. Whoa. Okay, better. That's the volume of the water that gets displaced by the cup. Now, here is something interesting. Here you have rho. This rho is the density of the fluid that it's in. We used it in our pressure equation for our gauge pressure here for the rho GH. And so this rho is actually the density of the fluid that the cup is in, which in this case is water. Now, one last move. Oh, this is so great. Okay, now, one last move. We got that the density, this is something that we know about density. We know that density is equal to mass per volume. And we know that density times volume gives us mass. Here I have the density of water times the volume of the water displaced, which means I can combine these two to say that this is the mass of the water that is displaced times G. Hey, the mass of the water that's displaced times G, mg, you know what that is. You know that that is Fg, or weight. And this is Archimedes' principle. Archimedes' principle. Remember, what did we even start out here at the beginning? We started out at the beginning talking about what the buoyant force is. What is the buoyant force on this object? The buoyant force on the object is the weight of the water that's moved out of the way for this object. That is Archimedes' principle. Archimedes' principle says that an object, I'll say this a few times so that you can get this written down. This is a definition. Do write it down. Archimedes' principle says that an object immersed in a fluid, will displace an amount of fluid whose weight will equal the buoyant force on that object. And one more time, definition for you. An object immersed in a fluid will displace an amount of fluid whose weight will equal the buoyant force on that object. In fewer words, Archimedes' principle says that the size of the buoyant force acting on an object equals the weight of the fluid that is displaced by that object. And that is Archimedes' principle and is, of course, most certainly worthy of your bag of tricks. Now, let's look at a little example here. Let me think about how I want to show this. This is kind of dangerous because I'm about to bring water near my computer. That is just a recipe for disaster. Okay, one moment here. Okay. Okay, one second. I'm going to make this thing big here. And now I'm going to show you this. Okay, ignore the mess that I have here. It's always a mess in here, okay? That's how I live my life. Okay, here I have, this is actually a quick little like preview, a little trailer for what your lab is going to be like. Here I have a little cup full of water, and I filled it up all the way to the brim, or all the way up to the brim of the spout, really. And here I have a little catch cup to catch any water that falls. Now, if I take this mass here, and I lower this mass into the water here, it's going to displace some water. So check it, it moves some of that water out of the way. When I lower it in, the water goes out of the little spout here. Then I can take my little mass out here, and you can see that in my little cup, actually, can you see? In my little cup, I have some water. That water that's in there is the amount of water that was displaced by this cube when I put this cube inside of the cup. So this, if I wanted to know how strong was the buoyant force acting on this mass when I lowered it into the fluid, or when I lowered it into the water, the strength of the buoyant force acting on this block is equal to the weight of this water. If I can hold this water in my hand and I can feel what the weight of this water feels like, the weight of this water here, well, I tried to show it to you, but that was a goofy and dumb thing to do. Who thought I could hold water in my hands? Not me. Well, no, yes, me. That is exactly what I thought. Okay. But the idea is the weight of that water as I'm holding it in my hand, that's how strong the force, that's how strong the buoyant force was that was acting on the little mass here. In other words, the more water that you displace, the stronger the buoyant force. Okay. Now, that is like part of the picture. That is a great start to the picture. That is the buoyant force. But what we have to talk about is how the buoyant force actually relates to objects. Why did I lose everything just now? It's because I moved everything out of the way and I made a mess. One second, let me actually clean up my mess really quick. One moment. Okay, now we're all cleaned up and good to go. So, here's the concept. Talking about the buoyant force is great, and understanding the buoyant force is great. The buoyant force is equal to the weight of the fluid displaced. But we got to relate that to whether or not something will sink or float. Here's the idea. If an object is submersed in a fluid, let me show you another object submersed in a fluid. This one will be a rubber ducky. That is a terrible rubber ducky. That's an embarrassing excuse for a rubber ducky. That looks like one of those like the little Peeps, or yeah, you know what I'm talking about, like the little Easter candy that gets just mauled in the box and it just kind of gets deformed and you're like, what even is that? That's what that looked like. Okay, here we have a rubber ducky. For some reason, I feel like it needs eyes on both sides. I understand that's not really how, well, but that, I think it made it worse. Anyway, here we have a rubber ducky sitting in the water. To know whether this rubber ducky will sink or float, we got to look at the forces that are acting on this rubber ducky right now. There are two forces that are acting on it. Well, there are a few forces, but there are really two main forces that are acting on this rubber ducky. First, the weight of this rubber ducky, gravity. Gravity is pulling the rubber ducky down. Then, the buoyant force is pushing the rubber ducky up. Now, remember, the buoyant force is really a combination of the pressure on the bottom and the pressure on the top, but we say the buoyant force is about the difference in pressure, and so we'll call it one force even though it's really the result of two different forces competing and the pressure on the bottom winning. But the buoyant force is pushing up, the weight of the rubber ducky is pulling down. Now, whether or not the rubber ducky sinks or floats depends on the battle that goes on between the buoyant force and the weight of the rubber ducky. The weight of the rubber ducky. If the weight of the rubber ducky, or whatever object you have in the water or in the fluid, we'll just call it an object so then it can be nice and generic. If the weight of the object is greater then the buoyant force, then the object will sink. Because the weight of the object will win out over the buoyant force. If the weight of the object is, let's do less than the buoyant force, then the buoyant force will win and it will launch the object upwards and it'll start moving upwards, 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 upwards. If, sorry, I gotta move this guy out of the way. Get out of the way, bruv. Excuse me. Okay. If the weight of the object is equal to the buoyant force, then the object will float. So, if the rubber ducky weighs more than the buoyant force, then it will sink down to the bottom of the bathtub. If the weight of the rubber ducky is way less than the buoyant force, then the buoyant force will win, and it'll send that little rubber ducky launched out of the water. That's what happens with my bathtub cup in the bathtub, is I push it down, but the buoyant force is stronger than the weight of that thing, so when I let it go, it goes flying upwards. This is also what happens with a balloon filled with helium. The balloon filled with helium, I started this and now I'm like, I need to finish it, but I'm actually going to pause this in the middle because I want to come back to the helium balloon because that's like a whole other thing. But this is what happens with the helium balloon, is basically that the helium balloon, the weight of the balloon is less than the buoyant force from the air, and the buoyant force from the air lifts that balloon up and launches it towards the sky. Then, if the weight of the object is equal to the buoyant force, then the object will float. Just kind of hovering. Now, floating doesn't necessarily mean that you're floating up on the surface. You could also float in the water like this, where you're sitting in the water, not moving up and not moving down. So floating just means not moving. And those three ideas are the guiding principles for whether an object sinks or floats. It's all about the battle that goes on between the buoyant force and the weight of the object. Okay, now, that is a lot of content, so we got a few questions to check how this is going for you. Here's my first one. Do a quick little check in your brain. Okay, wait, oh gosh, that is annoying. Go away. Be like normal. Okay, yay, wow, it listened. Okay, here I have a wooden dowel and a barbell. They are both approximately, it's kind of hard for you to see here, but they're both approximately the same size. Now, if I take this wooden dowel and this barbell, and I set them both in a fish tank full of water, then the barbell will sink down towards the bottom and hit the bottom of the fish tank. So the barbell sits on the bottom of the fish tank. The dowel, meanwhile, will sit up at the top of the fish tank and will float along the top of the water like this. Here's my first question for you. Do discuss it with a neighbor or with a friend. Which one experiences a greater buoyant force? The barbell sitting down on the bottom of the fish tank, or the wooden dowel floating up along the top of the fish tank? I'll draw a picture while you discuss it. Whoa. If I can get everything moved out of the way here. Are you discussing? You should be discussing. Discuss or think and then discuss is probably the right order of operations there. Oh gosh. Oh my GOSH. Don't do that. No, stop. Oh no. I fear the computer's going to give me a terrible crisis moment. One moment, please. Okay, here is a picture. This is the wooden dowel floating up along the surface of the water, and here's the barbell sitting at the bottom of the fish tank. Who experiences the greater buoyant force? The barbell. You say, what, Miss Wilson? But it's sinking. It's down at the bottom. But check it out. The one that experiences the greater buoyant force is the one that displaces more fluid. Archimedes' principle says that the buoyant force is equal to the weight of the fluid that's displaced. Take a look. Who's displacing more water? If the wooden dowel is floating so that half of it is out of the water and half of it is in the water, it's only displacing, wait, let me show you here. It's only displacing this much water. Meanwhile, the barbell, which is totally submerged, is displacing this much water. So the barbell displaces more water, which means the buoyant force on the barbell is greater. But you're saying, Miss Wilson, then why does it sink? Because remember, it's about the comparison between the buoyant force and the weight of the object. The wooden dowel does displace less water, so the buoyant force is less. But it needs less buoyant force in order to float because it weighs so much less. So the weight of the dowel is equal to the weight of the small amount of water that it's displacing. It doesn't need to displace any more water. If it were to displace more water, the buoyant force would be too big and the thing would get launched. So because the dowel is so light, it doesn't need to displace that much water. If it, well, I'm just going to get redundant, so I'm not even going to talk again. Okay, the barbell, on the other hand, the barbell is displacing a lot of water. But the weight of the barbell is so big that even though it's displacing a lot of water, the weight of the barbell is still greater than the weight of the water that it's displacing. And so if I put the barbell in the water, that thing is just going to sink straight on down. Because even though it's displacing more water, it's still not enough to overcome its weight. Remember two principles here. First, that the buoyant force is equal to the weight of the fluid that you displace. And second, that the thing that actually determines whether something sinks or floats is not necessarily how big the buoyant force is. It's how the weight of the water displaced compares to the weight of the object. Okay. Here's another example. Here's the next question for you. I got a total of 3 questions to figure out how this whole concept is going for you. First one is the dowel and the dumbbell question. Here's the second one. Suppose that a ship sails from fresh water into salt water. 2 questions. When the ship sails from fresh water into salt water, does it float higher in the water or lower in the water? And second, is the buoyant force on the ship greater, less, or the same? Tell your neighbor, ship sails from fresh water into salt water. Now, one thing that you might need to know to be able to answer this question is you would need to know that the density of salt water is greater than the density of water without salt. Or what we would call fresh water, I suppose. Okay, tell your neighbor. Probably pause the video here. Take a quick moment. What happens to the ship? Does it float higher in the water, lower in the water? And then also, what happens to the buoyant force? Take a minute, go ahead and pause, talk to your neighbor about it. Okay. When the ship goes from fresh water into salt water, it'll float higher in the salt water than it did in the fresh water. Is that what you said? Let's start with this other question. Which buoyant force needs to be greater? The buoyant force in the fresh water or the buoyant force in the salt water? The answer is the same. isn't the boat floating in the fresh water? So when it floats in the fresh water, the buoyant force has to equal the weight of the boat. But then when it goes into the salt water, it's still floating. And in order to float, whoa, move my face. In order to float, the buoyant force has to equal the weight of the boat. So in both cases, because it's floating, the buoyant force has to be the same as the weight of the boat. If the buoyant force got bigger, it would be launching it out of the water. If the buoyant force got smaller, then the boat would be sinking down to the bottom. The buoyant force has to equal the weight of the boat in both cases, otherwise the boat won't, well, float. But here's the difference. The size of the buoyant force equals the weight of the fluid displaced. In the fresh water is less dense. The boat needs to displace an amount of water. It needs to move the water out of the way that weighs as much as the boat weighs. So the amount of water that the boat displaces has to equal the weight of the boat. In the first situation, the boat has to displace this much water in order for that water to equal the weight of the boat. But salt water is more dense than fresh water. So you don't have to displace as much of it because it's heavier. In order to displace an amount of salt water that's equal to the weight of the boat, that doesn't require as much water to be displaced because the water is heavier. And so the boat will float higher up so that it displaces less salt water. It displaces less salt water because it takes less salt water to have the same weight as the weight of the boat. So the buoyant force stays the same, but the boat displaces less water because it doesn't take as much water to equal the weight of the boat since the water is heavier. That's the idea. One last question for you, or one last set of questions for you to kind of test how these things are going for you. Here it is. You got a helium balloon, one of those that you take home from Red Robin, and you put it in your bedroom. You remember this from your childhood, and you would put it right next to your bed, and it would float up towards the ceiling, and then you would have to get your parent to come and pull it down for you, and they'd pull it down for you, and you'd say, wow, thanks so much, and then you'd let go of the string again, and then it would go back towards the ceiling, and then they had to come help you. So you got your helium balloon. It starts out on the ceiling of your bedroom, and then you go to sleep at night, and then you wake up in the morning, and you look up, and your helium balloon isn't at the ceiling anymore. It's floating down just a little bit lower. Here's a question for you. While you were sleeping, what happened to the helium balloon? What happened to the weight of the balloon? What happened to the buoyant force on the balloon? And why is it now lower down than it was before? Go ahead, take a quick moment, tell your neighbor, I'm going to pull up a picture. Okay, what happened overnight? The helium balloon leaked out air. It had more helium in it, and now it has less helium in it. Now, some of you are saying the helium balloon leaked out air and it got heavier. True or false? False. The balloon just lost mass. It had more mass, and now it has less mass. And so it actually just lost weight. It now weighs less than it did before. Because before it had more helium, now it has less helium. Helium's not heavy, but it still is something. It still weighs something. And now it weighs less because there's literally just less of it. So it does weigh less now than it did before. Wait, let me write that here for you. Okay, let's see. The weight of the balloon is less. But, oh gosh, I had to be able to spell balloon. The weight of the balloon is less. But, more significantly, when it lost helium, it lost some of its weight, so its weight went down. But what else went down is its volume. And the volume of the balloon is now substantially less. Oh gosh. Hey, how do balloons float in the first place? A helium balloon floats by displacing a certain amount of air, which is a fluid. It displaces the air, and when it displaces the air, normally the weight of the air that's displaced is greater than the weight of the balloon. So normally that means that the buoyant force acting on the balloon, which is the weight of the air that's displaced, is greater than the balloon. But when the balloon shrinks and the volume of the balloon is less, now the balloon starts displacing less air. Because it's not taking up as much space. And so it displaces less air, which means that the weight of the air that's displaced is less, which means that the buoyant force acting on the balloon is less. And so, even though the weight of the balloon is less, the buoyant force acting on the balloon is more or less. If that makes any sense. So here's what happens to the balloon. The balloon used to be up here. You can see I kind of drew gray. I don't actually know if you can see this, but I kind of tried to draw gray here so that you could see the air in your room. You know that the air that's up at the top of your room is less dense, and the air that's down at the bottom of your room is more dense. You could talk about this for a lot of different reasons, but the air that's more dense goes down to the bottom of your room, and the air that's less dense goes up to the top of your room. You could think about this in terms of pressure as well. But so the air down here is more dense. So the density of air here is higher. And up here at the top of your room, the density of the air is lower. So the reason why your balloon sinks is your balloon goes to a spot that is lower in the air. If it's lower in the air, then the density of the air is higher. And if the density of the air is higher, then the weight of the air that it displaces is slightly more. So it floats down to a place where the air is more dense, so that then at this lower spot in the room, then the weight of the air displaced here equals the buoyant force, which equals the weight of the balloon. So, you'll notice, you wake up in the morning and the balloon is still floating, but it's not floating up at your ceiling, it's floating like halfway in the middle of your room. It's not that it's not floating, it's still floating, so the buoyant force is still equal to the weight of the balloon. But your balloon had to move downwards to where the air is more dense so that it could displace, so that the amount of air that it displaces is still equal to its weight. Then, after a few more mornings, you wake up and your balloon is on the ground all the way down. At that point, when you wake up in the morning and your balloon is all the way on the floor, and it's kind of just a shriveled little thing at that point, it's actually like a very sad looking thing, something like this. When your balloon is all the way a little squished down on the floor, it lost a lot of weight because it lost a lot of helium. But it also lost a lot of volume, and because it lost so much volume, now it doesn't matter where it is in the room. Even the most dense of air, the densest of air, is not enough. It cannot displace, because its volume is so small, it cannot displace enough of the most dense air to equal its weight. And so that is when the weight of the balloon wins, and the weight of the balloon is now greater than the buoyant force because it's greater than the weight of the air that it displaces, because it's so small that it can't really displace that much air, and so then the balloon sinks. Okay, those were our 3 conceptual practice problems to kind of work with Archimedes' principle and the buoyant force. What we're going to do next is we're going to do a little bit of a practice problem. Let me go ahead and get that pulled up here. Now, suppose that you go to the bottom of a freshwater lagoon and you find a giant piece of gold at the bottom of the freshwater lagoon. Now, normally, this thing would be enormous and very, very hard to lift. It must have belonged to some pirates long ago, but now it's yours. If you can get it out of the lagoon, that is. You take some quick measurements and you find that the length of this thing is 73 centimeters, the width of this thing is 53 centimeters, and the height of this thing is 7 centimeters. And that is the size of this bar of gold. Now, normally, this would be very, very heavy to lift, but here's the question. How much force will it take to lift it off the bottom of the lagoon? This introduces this concept that we call apparent weight. You know that when something's in the water, it doesn't feel near as heavy as it normally is, actually. Do you remember this? Like when you'd go to the pool with your cousin Valerie, and your cousin Valerie would be like, throw me, and you'd be like, yeah, okay, fine. And you would never be able to, like, really pick up Valerie and throw her like crazy as hard as you can. But when Valerie's in the water, it's really very easy to pick up Valerie because Valerie feels so much lighter in the water. Why does she feel so much lighter? Well, because when Valerie's in the water, or if you have a chest of gold in the water, let me draw a quick FBD. We got a little free body diagram. If you got a box of gold in the water, or your cousin is in the water, then their weight, whoa, that is for serious. Let's go with a little pen here, not that whole big marker situation. Their weight is pulling them down. But the buoyant force is helping them up. So, the amount of force that it takes to lift something is normally as much as it weighs. But if you are going to lift something and that thing is in a fluid so that it's experiencing a buoyant force, then you don't have to lift as much because the buoyant force is helping you to lift. So, together, the buoyant force combined with your force of lift, that has to be as much as it weighs. But because the buoyant force is helping you, you lift with less. We call this here, like how much you would have to lift it with, or this would also be like what a scale says if you put it on a bathroom scale. We call that the apparent weight, because it's how much it feels like it weighs. Normally, something weighs as much as it takes to lift it. But here, it feels like it takes a certain force to lift it. That's not how much it actually weighs. That's how much it seems to weigh when the buoyant force is helping you. So this is the concept of apparent weight. We say that if you are going to lift this thing, then we can define our axes like this. I'm going to call up the positive direction. And we would say, if you're going to lift this thing, then the net force, if you want to lift it at a nice constant velocity, the net force is going to be 0, which means that the force for lifting it plus the buoyant force, those two together, whoops, wait, let me do this better, minus the weight, the actual real life weight of the object, all of those will equal 0. Or in other words, the force to lift it and the buoyant force together are going to together equal the weight because the buoyant force is helping you to lift. If you're seeing for this particular problem, we're solving to see how much force is it going to take to lift this thing. So to lift this thing, we need to do how much it weighs minus the buoyant force. Okay, now, here's the problem. I didn't give you the mass of the gold at all. I gave you the dimensions of the gold bar, and you, of course, know deep down in your heart that the density of gold is equal to 19,300 kilograms per meter cubed. Or you know this because you looked on page 275. Oh, I lost the 275 of your textbook, where there is a little table that tells you the densities of common substances off on the right-hand side. That table might be useful to you in the near future. So, you know that the force that it takes to lift something is equal to the weight of this thing minus the buoyant force on it, but I didn't give you the weight of this thing. I gave you the density of it, or you know the density of it, and you know the volume of it. So, here's what I'm thinking. I'm thinking that the weight of this object is going to be the mass of the gold times g. Then, okay, yeah, we can deal with the buoyant force now. The buoyant force, we know, is going to equal the weight of the water that's being displaced by the gold. Well, the weight of the water displaced by the gold would be the mass of the water that's displaced by the gold times g. Now, here's the problem. I don't know the mass of the gold, and I don't know the mass of the water that's displaced. But I do know things about densities, and I do know things about volume. Off to the side here, above my gold bar, I'm going to do a little bit of work. Here's what I know. I know that density is equal to mass over volume. I can use this to find the mass by saying that then the mass of something would equal its density times its volume. Well, the mass of the gold would equal the density of the gold times the volume of the gold times g. The mass of the water displaced would be the density of water times the volume of the water that's displaced times g. Well, in this case, check it out. Isn't the gold displacing as much water as its own volume? So the volume of the gold is the volume of the water that's displaced. So I can change this to say that I have the density of gold times the volume of the gold times g minus the density of water times the volume of the water that's displaced. But the volume of water that's displaced is the volume of gold times g. Now you'll notice that we have some common factors here, so if you want to, you can pull them out. I'm going to do that for the sake of an illustration purpose so that you can see this here. Do you see that we have the density of gold minus the density of water times the volume of gold times g? And here is what I want you to see here. Do you see that what you learned as a child is totally true? That it all comes down to densities. You have the density of gold minus the density of water. Their relative densities will determine whether this sinks or floats. Do you see how if the density of gold is greater than the density of water, I'll end up with a positive number for F lift, which means I have to put in some water to, or I have to put in some force to lift this thing, meaning it's sinking. But if the density of water was greater than the density of gold, then I'd get a negative number here, which means I actually don't need to put in any force at all. In fact, in order to lift it, I would need to put my hands down to try to stop it from flying up so fast. I would have to create a negative force to keep it going up at a constant velocity. In other words, if the density of the water was greater than the density of the gold, this thing would go launching up towards the surface. And if they were equal to each other, then the force that it would take to lift it would be 0, because these two would cancel out with each other. And so what you learned in your childhood about densities and that making the difference, that is still true. That is still true today. Now, last little step here. I didn't give you the volume of the gold. Instead, you're going to have to find that. So we do the density of the gold minus the density of water. And then you know the volume of a little rectangular prism like this. You're just going to do area of the base times the height, or length times width times height, like this, times g. Then we can plug in numbers and get to a final answer. When we plug in numbers, don't forget you got a quick unit conversion that you got to do here. I'm going to spare you some time here, and I will tell you that you would have to lift with a force of 490 newtons, which is about 110 pounds. if you can lift 110 pounds, you could have the gold. Some of you are like, but I'm not going for gold today. Okay, that is all for today, folks. Let me tell you a little bit about your homework assignment, and then we'll be done. Your homework assignment for tonight is page 279, numbers 1 through 4. On this homework assignment, your textbook has a way to do these problems. Please do not do the problems the textbook way. Please do the problems the way that we just showed together in this video here. This is going to be the formatting for how you do these kinds of problems. I highly, highly recommend that you draw pictures. You're going to need to be very thoughtful, and you're really going to need to think through how to do these problems. I am going to be posting an answer key online for these problems. Please use the answer key wisely. I'm actually going to post 2 answer keys. The first answer key is going to be just the answers, and the second answer key is going to be the answers with the solutions. I'll also post a document online that's called How to Use an Answer Key. What you should be doing is you should try the problem all by yourself, check your final answer, see how your final answer compares to the answer on the final answer sheet. If those answers match, you're probably good to go. If not, then you need to go back to the solutions manual, kind of check through your work, see where you went wrong. If you get stuck, you can use the solutions page to kind of help you find your way. But anything that comes from the answer key needs to be done in pen. Anything that comes from your brain, do in pencil. You will not lose any points for anything that you do in pen. You also do need to read, print, and bring our lab for next time. And that's all for today, folks. I do hope that you have a wonderful, wonderful rest of your day. And yeah, wow, that's pretty much it. Okay, bye, good people.